Anyway, my name is Michael Adler. I'm a member of the board of the Geologists of Jackson Hole, and I'd like to welcome you to our Zoom presentation. This one is also live at the St. John's Episcopal Church in Jackson. Well, we're happy you can join us tonight. Tonight we have David Larsen from Occidental College presenting a talk on studies of the Teton Fault seismicity using mountain front lake sediment data. Our next talk is going to be on April 19th at 6 p.m. Also at St. John's, and it'll be on Zoom as well. And that talk is going to be Probing the Ancient History of the Northern Rockies by Kendra Murray of Idaho State University. If you want to join any of our upcoming meetings on Zoom or in person, and we do believe they will be in person going forward from here, you can get all that information from the newsletter or by going to our website. If you're not getting our newsletter and you would like to, go to our webpage, geologistsofjacksonhole.org, and sign up. If you happen to miss one of our presentations, Elizabeth Kingwell is currently recording this one, and they are all loaded up after the presentation, so you can check them out. Also, if you're a member and you haven't renewed your dues, we'd appreciate it if you would do that. As far as questions go, this is going to be an interesting meeting because we have both a live room as well as people on Zoom. But if you're on Zoom, you want to use the chat feature, and you can do that anytime during the Zoom presentation. So to do that, if you move your mouse around the bottom of the screen, menus will appear, and then just hit chat. And when you're doing that, you want to send any messages to Mike Schur, because Mike will be actually reading the questions to Darren at the end of the talk.
I'm sorry, Mike Adler.
Yeah.
This is Cynthia. They need to send chat questions on Zoom to me, to Cynthia Blankenship.
Okay, I'm sorry.
Yeah, that's okay. Mike Schur will handle the questions at the church.
I got it. Okay. All right. Okay. So sorry about that, folks. Send them to Cynthia Blankenship. Okay, now I'd like to introduce Mike Schur, who will introduce our speaker. Mike is a member of the board of the Geologists of Jackson Hole, works in our outreach program, and has given several Tuesday presentations. So Mike, would you take it from here?
Yes, thank you, Mike. So if I could ask our audience here in the church to mute your cell phones. And this speaker is really good. So if you're loud, it actually interferes with everybody else hearing. And so I'd ask that people keep the comments and conversations as low as possible. One correction, 2 weeks from now on April 19th, Kendra Murray's talk will only be via Zoom. She's not able to make it here. The talk is still on, but don't show up at the church. Just stay home and watch it. And it should be a really interesting talk. So we're very fortunate to have Darren back for a third Tuesday night program. The other two were extremely interesting and informative. I'm sure this one will be as well. Quick bio, Darren got his bachelor's in geology and biological sciences at Colby College in Maine, his PhD at the University of Colorado Boulder and the University of Iceland. He's currently assistant professor at Occidental College in Southern California, has numerous geologic interests. I won't even read them all. Same with the publications, where he wouldn't have time to talk. He teaches all these great classes, which I would love to actually attend: evolution of the earth, field geology, sedimentary geology. He's done field work all over the planet, including New Zealand, South America, Canada, everywhere else. So please join me in welcoming tonight's speaker, Darren Larsen.
Thank you, Mike, and thanks everybody for joining both here and wherever you might be zooming in from. So we have a nice group here of around 20 people here in live in town, but I understand there's a bunch of folks watching from Zoom. And so of course, I'll be mostly addressing the folks who are here, but I encourage questions from folks on Zoom as well. For the folks who are interested or something is unclear tonight, I think it's a small enough group where, and kind of intimate enough where if you feel like you need some clarification or something doesn't make sense, I would appreciate it if you just maybe raise your hand and ask me rather than remain confused throughout the talk. All right, so yeah, thank you once again for being here. It's a pleasure. Thanks for the introduction, Mike. This is actually the third time I've been able to have the opportunity to present to the geologists of Jackson Hole, which is just a fantastic opportunity for me. So I think we want to have my video being shown on that screen if folks want to be able to watch from Zoom. I'm not sure why we're having someone else up here, but we can, if that person can mute themselves, I can mute these people. Okay. Nope. If I start talking, maybe my voice will show up instead of Joanne's iPad. Or I can do this, but it sort of detracts from the slides quite a bit.
What you're seeing up there is just coming from this little monitor.
Now, I'm not sure why my video doesn't show as the primary video, but
Ask Cynthia if she sees the slides.
Cynthia, can you see my slides and is my video of myself
Yes.
coming through?
Yes, I see your slide, your starting slide, and I see you.
All right. Okay, great. We just see a different image on the Zoom screen on our end, but of course everyone here can see me just fine. So we'll just continue right along. Sorry for the delay.
Can you speak up just a little bit there?
Absolutely.
Thank you.
Okay. All right. So I'm thanking everyone. I'm thanking the geologists of Jackson Hole, but of course I also want to thank everyone who's collaborated with me on these projects or helped out in the field or in the lab, as well as funding institutions who have supported this work. And that includes the National Science Foundation, the National Park Service, the Grand Teton Association, and a variety of different funding groups. And all of the work that I'm showing you today, all of these data and these results could not have happened without tremendous support from friends and colleagues and students and field assistants to collect a lot of the data that I'll be showing you. So thank you, everyone. I thought I would start this talk placing this research within the context of landscape evolution. And so we can ask a question when we see a landscape like this one shown here. We can ask a question like, how did this landscape form, right? And I put form in quotations because I think we all would agree that this landscape, unlike the photograph that was taken of it, was not just immediately created, right? It is the product of a whole slew of forces and surface processes and deep earth processes, which are integrated and evolving through time. So instead of asking how a landscape like this forms, we can ask how it's evolved or how it's going to continue to evolve. And when we think on those terms, we begin to invoke processes that result in the creation of landscapes or the creation of terrain or topography, deep earth processes that drive uplift, and processes which result, surface processes which result in landscape modification and the weathering and erosion and sculpting of landscapes such as this that was captured around 80 years ago to this day, and maybe around this time of year as well. So within that context, I just have a few bullets here related to landscape evolution. So these two forces, these different forces that are in some sense competing with each other, forces that drive uplift, tectonic forces that create topography, and forces that result in the denudation or destruction of landscapes through weathering and erosion. And many of those processes are modulated by climate forces, climate drivers. So climate and tectonism influence the geomorphic development of mountain landscapes through space and through time. Alpine ecosystems in these landscapes are very sensitive to disturbance associated with both of these drivers, climate drivers and tectonic drivers. So climate change, tectonic activity, and now more recently, human activity can generate disturbances that can severely impact these alpine ecosystems. And these impacts pose serious challenges for human adaptation, hazard assessments, and resource conservation efforts. So this work I'm going to be showing you today is from a recent collaborative grant with a few PIs that is aimed at quantifying the relative roles of tectonic activity and climate as drivers of glacial, interglacial landscape change here in the Teton Range. And I've listed my co-Is on this grant, Joseph Licciardi at UNH and Glenn Thackeray at Idaho State University, as well as important collaborators of this project, Mark Zellman, Sarah Crump, Alia Lesnick, Aria Blum, and Amelia Muscat. So students, collaborators, postdocs at various institutions. And the overarching goal of this project, including what I'll be showing you today, is to really try and understand the role of tectonic and climate processes in shaping mountain landscapes and in controlling the rates and magnitude of sediment production, transport, and deposition in alpine landscapes. All surface processes that we know of.
Wait.
All surface process. I'm just going to remind everyone on Zoom to mute their microphones if they can. So that mute button is in the lower left corner as you're looking at your Zoom screen. There's a little mute with a microphone icon. And if you click that, there should be a red dash that goes through that icon. So you're muted because we're hearing some feedback on our end. So surface processes on planet Earth result in the production, transportation, and eventual deposition of sediment. And what we'll be talking about today are ways that we can evaluate these sediment deposits to say something about those past surface processes and how they operated through time. This work is very much building on a ever-growing body of literature that's been performed here in the Teton Range, in the greater Yellowstone ecosystem and Grand Teton National Park, that's been focused on the tectonic, geomorphologic, and glacier geologic history. And I know many folks in this room know some of these authors personally or are familiar with their work and so forth. So yeah, no science is done in a vacuum. We are very much building on that earlier body of work. So the objective here today are to use lake sediments. So we talked about the importance of sediments. In this case, we're talking about lake sediments, sediments accumulating in lake basins to quantify the influence of climate-driven disturbances and changes here in the Teton Range. For example, those associated with deglaciation, wildfires, droughts, moisture balance changes, vegetative shifts, and so forth. And also tectonic-driven disturbances. For example, those associated with earthquakes or landslides, to understand the alpine environments and landscape evolution of the Tetons. And so of course today, as you saw in the title of the talk, we're going to be focusing on this second bullet here. And that map on the bottom of the screen is kind of an oblique satellite image just from Google Earth showing the eastern range front of the central Teton Range, as well as a few of the lake sites that we'll be visiting in this talk. If I can get my laser pointer going here. Oh, it doesn't show up on the TV. I think most of you are familiar with a map or an image like this. What I wanted to point out here is that we're targeting a few different catchments, and all of these lake sites that we've been working at for this project are highlighted in with those yellow dots. I also wanted to highlight the fault scarp of the Teton Fault there in black. So speaking of faults, I thought it would be worthwhile to just remind us of the tectonic setting of where we are here in Jackson, Wyoming, but also within the Western US. So this is a map of the Western US, and I've just overprinted the fault lines from the US Geological Survey here, shown in red. It might be a little bit hard to see on that screen, but in general, the Western US is characterized by an active margin along the western perimeter of the continent. So these are plate boundaries, major fault systems. But then interior to that, we have the Basin and Range Province, which is characterized by a series of extensional tectonism that's characterized by normal faulting. And here, I can't point with my laser pointer, but maybe I'll just show all of you. So here we are.
Use a cursor.
Yeah, just look. There we go. Thank you. So here we are in the very northeastern edge of the Basin and Range Province. Also from the same site, I'm now overlying the recent earthquake activity along these faults. So faults, as you know, are breaks in the crust, which can sometimes result in movement along those planes, and that movement can be expressed as an earthquake. And so, as you would imagine, these fault lines here are associated with earthquake events. And so this is the earthquake occurrence for all earthquakes, I believe, greater than magnitude 2.0 or something like that. So essentially all moderate to large earthquakes of the last 30 days. Yeah, that might be all earthquakes of any magnitude as recorded. And so because of that, we then can generate hazard maps, earthquake hazard maps, and that's what's shown here. And as you would expect, locations where there have been recent earthquakes have high earthquake hazard. So the major fault planes that you would think of when you're thinking of extreme earthquake hazards, those in, for example, the San Andreas fault line or maybe Cascadia is where your eye is drawn. But you notice there's quite high earthquake hazard and earthquake occurrence here in the Northeast Basin and Range as well, associated with some of these normal faults that are more nearby. So here's a map zooming into just the state of Wyoming. This is from the Wyoming Geological Survey, showing all earthquakes of magnitude 2.5 or greater over the last roughly 150 years. And so as you would expect, living here, right, Yellowstone is a region of high seismicity, and clearly there's great clustering of earthquakes there. And then some more earthquakes scattered throughout the state, but generally a concentration on the northwestern boundary of the state. Interestingly, the Teton Fault itself has been relatively quiet over the last 150 years. There has been very little earthquake activity along the Teton Fault itself, which might be interesting considering that's kind of exactly what we'll be talking about with this presentation. So it has been noted for being an active fault with potentially high risk and hazard associated with it. However, it's been relatively quiet or experienced relative quiescence for the historical record. So let's talk a little bit more about the Teton Fault in particular. It's a major range bounding fault. So similar to many of the faults in the Basin and Range Province, many of those ranges are bounded by an active normal fault, as is here in the Tetons. It's an eastward dipping normal fault that extends for roughly 70 kilometers along the Eastern Range front. So running right through the middle of Grand Teton National Park. And it's shown here on this map, which is just an aerial map, bird's eye view of the Teton Range here, and the fault is shown with that red line. Again, it's considered to be an active fault despite no major earthquakes in recent history. However, the long-term activity has also been investigated, and it's thought that the orogenesis of the mountain range is related to the onset of faulting of the Teton Fault, and that's associated with Basin and Range extension beginning over 10 million years ago. It's also thought that the migration of the Yellowstone hotspot has influenced the pattern of fault activity and fault dynamics. So that is still very much an active field of investigation. Based on these relative uncertainty regarding the timing of initiation of faulting and then the total magnitude of displacement, there's quite a big range in the long-term average slip rate for the Teton Fault, ranging from less than 0.5 millimeter per year long-term to over 1.2 millimeters per year long-term slip rate. Again, those estimates are really just derived by the total length of displacement divided by the length of time that displacement has been occurring. Because those two variables are still not that well constrained, we don't have great constraints on this long-term slip rate, but we have pretty good estimates. And certainly that there are folks who are actively investigating this over the next few years. Certainly over the next few decades, we're going to learn more and more about the initiation of faulting here in the Teton Range. So here's another view of the mountains. This is an oblique aerial view, kind of with looking towards the southwest. We're looking over the Teton Valley, the hanging block of this normal fault, onto the Teton Range itself, the footwall that's been upthrust. And I wanted to highlight this. I really like this image here because I think it does a good job of showing this combination of tectonic activity driving mountain uplift and then forces that have sculpted the range into this iconic landscape that we know today. In particular, I wanted to point out this series of valleys that transect the range here, both on the eastern side and on the western side, draining into Idaho, into Teton Valley along the western slope. So this integration between the glacier geomorphology and tectonic history is something that'll play out in this presentation. The mountains themselves, again, have been shaped by tectonism and periodic Quaternary glaciation. So the Quaternary period, as some of you know, is the last roughly 2.5 million years of Earth history. And it's really defined as this relatively recent period in Earth's past where we've been experiencing these successive glacial and interglacial periods. During the most recent glacial period, which around here is referred to as the Pinedale glaciation, because the type section for these glacier deposits is just down the road. The Tetons in adjacent Yellowstone region contain one of the largest mountain glacier and ice complexes in the Western US, outside of the great ice caps, or ice sheets rather, that blanketed most of Canada, the Laurentide and Cordilleran ice sheets. And so here you can see that same map of the Western US, and I've highlighted the greater Yellowstone and Teton Ice Complex there. So it was a large mass of ice. This configuration of glacial ice persisted for many thousands of years, tens of thousands of years during the last glacial episode in some form of another. And then eventually, of course, it disappeared in response to climate warming at the end of the last ice age. But those glaciers are very efficient or aggressive agents of erosion, and they're able to create landforms that persist to this day. And the offset of these glacially derived landforms by the Teton Fault is one of our key lines of evidence to understand that the fault has been very active since this period of glaciation. So essentially since deglaciation, which has been timed to about 15,000 years ago. So we're able to look at the offsets of these glacier features, which I've shown a figure here by my colleague, Joe Licciardi, who graciously presented this image here, which is unfortunately blocked by our Zoom bar. Let's move that out of the way.
Darren, we can see it.
We're having, thank you. We're having a hard time seeing it here on our end. So that figure at the bottom of the text there is an image that's been overlain with draped with LiDAR that Joe provided, that he created, showing that the Teton Fault cross-cutting these kind of really prominent glacier deposits that have been left behind and preserved since deglaciation. Joe has been targeting these moraine features to determine their age. And he's been generating a tremendous amount of data related to the chronology of glacial activity, but also related to the chronology of faulting, because again, the fault scarp itself is cross-cutting these glacier features. So it's very important to determine their age. Here we're showing 3 terminal moraines and their associated lateral moraines as the glaciers advanced out of those 3 valleys there in the central Teton Range and Grand Teton National Park. That's Avalanche Canyon, Garnet Canyon, and Glacier Gulch. Sorry. Okay, from the work that Joe has been producing related to these glacier chronologies, we think that these glaciers were retreating rapidly at the end of the last ice age, beginning around 15,000 years ago. And again, they left these landforms behind. Since that time, faulting, displacement along the Teton Fault has created these beautiful offset features of those glacier deposits, in some cases up to 30 meters tall, and they're displacing those moraines based on the age of the moraines at around 15,000 years ago, and the magnitude of displacement. We can play that same game and derive a long-term rate of distance over time, which works out to about 2 millimeters per year, which if you think back to those long-term averages that we discussed over the past few million years, this is quite a bit faster than that, much, much faster than that. So this is a very active fault over this time period. And yet we don't have evidence for this type of slip rate over the long-term geologic past, nor have we seen or experienced much faulting in the historical record. So it's a little bit of an enigma here. So to further understand this, we need to generate a paleoseismic record, a record that we can use to understand the seismic history of the fault. And for the Teton Fault, that's been pieced together from a few sources, but it remains largely incomplete. One of the primary sources for generating paleoseismic histories along normal faults in particular, or really any faults, are trench excavations. And some of you may be familiar with this. This is kind of the tried and true or paradigm method for constructing paleoseismic histories. And the idea here being with the Teton Fault, or a normal fault similar to that, is to excavate a trench, to dig a trench perpendicular to the fault scarp and identify horizons that have been offset through successive earthquake events. So ruptures along the fault resulting in surface displacement can offset horizons, which can be identified in the sidewall of a trench and dated. And so here I'm showing you again a map of the Teton Range where there have been 5 trench excavations performed along much of the trace of the Teton Fault. In the south, by Teton Pass there was a trench excavated at Ski Lake. And then to the north here in Teton Village at the base of the popular Buffalo Bowl ski run, as well as at Granite Canyon. That was the original fault trench here in the Tetons that was performed by folks at the University of Utah. And that was kind of the initial paleoseismic investigation to the Teton Fault, which really kind of gave rise to all of this subsequent work. And then here at Lee Lake, and then up north of Jackson Lake there at Steamboat Mountain. So the magnitude of those excavations varies. In some cases, they were literally dug by hand with shovels and essentially a team of students. In other cases, like what is shown here at Buffalo Bowl at the Teton Village, that was a major backhoe excavation. And so that is the Buffalo Bowl excavation that was really led by the USGS and colleagues. And that is a major trench excavation, obviously, that was performed at the fault there. And then these figures on the bottom, that's just a simple block diagram to kind of remind us of the configuration of a normal fault here, where we see the valley, in this case of Jackson Hole, subsiding relative to the mountain block. And the idea would be to identify horizons such as this orange or yellow horizon that have been offset by an earthquake event. Here on the bottom is a figure taken from Darren et al. 2020, where they were performing this exact method just in real life, essentially. And I just stole that there from his paper for demonstration purposes. Yeah, John.
Or you got Buffalo Bowl and Granite Canyon. What are the 3 sets of numbers after each one of them?
Yeah, great question. So
Can you repeat the question?
Yeah, so there was a question here in the audience asking to speak to some of the numbers associated with all of those 4 bullets in bold. And those are the ages of rupture events. So those are the ages of earthquake events. They're expressed in Ka or kilo annum. Those are thousands of years ago. So for example, at that Buffalo Bowl site, they found evidence for 3 surface rupturing earthquakes that they then dated using organic remains contained in the sidewalls of those trenches associated with those offset horizons to roughly 9.9 Ka or 1,000 years ago, 7.1 1,000 years ago, and 4.6 1,000 years ago. The numbers in parentheses there, that's the standard deviation, the 1 sigma standard deviation. So essentially the age envelope associated with the timing of those events. At Granite Canyon, again, that original trench site, they found evidence for 2 rupture events at roughly 8.1 and 6.3 thousand years ago. To the north at Lee Lake, there were 2 earthquake events dated to 10.0 and 5.9. And then even further north, 2 rupture events at 9.7 and 5.5. If you squint at all of these numbers and summarize this, all of these trench data sets provide evidence for at least 3 surface rupturing earthquakes of the Teton Fault at roughly 10, 8, and 5 thousand years ago. And is well summarized in this Occidental 2020 paper. Question?
Can you turn us around here so we can see what direction is the trench transecting the fault?
So the question is asking about the orientation of these excavations along the Teton Fault. In this case, that trench image there was dug perpendicular to the fault scarp. So you're very much looking uphill. The fault is running along the base of the hill, and that's dug perpendicular to the trace of the fault.
And you can see the elevation of the scarp as you go through the trench.
In the sidewalls. So you can see, the question was about the identifying the scarp itself in these excavations. And you can see that exposed in the sidewalls of the trench, not along the floor of the trench itself. Yeah. The idea is you're trying to cut down, excavate down across the fault, and then have this this image here on the bottom of the slide is showing the sidewall of a trench excavation, and that red line is marking the Teton Fault itself.
Thank you.
You're welcome. So these, importantly, these trench excavations not only allow us to determine the timing of past earthquake events, but we can, similar to this question here, we can determine the amount of displacement that occurred during any individual rupture event. That amount of displacement speaks to the magnitude of the earthquake. So we can determine, we can infer the past magnitude of these earthquake events that occurred. Based on that evidence, these scarp forming earthquakes are considered to be pretty major, earthquakes of magnitude 7 or greater. So all of this trench data and then measurements of these surface expressions of fault offset of these glacial deposits suggest that the majority of this vertical offset that occurred since deglaciation was accomplished early on, almost immediately following deglaciation, and seemed to be active up until about 8,000 years ago. So kind of in the early half of our present interglacial period. And then it's been much more quiet ever since. And so this hints at some sort of irregular recurrence interval of earthquakes and perhaps relationship between deglaciation itself and fault slip rates. And indeed, this has been put forth by modeling studies, which have demonstrated that the melting of the Yellowstone and Teton ice masses and unloading of the crust caused a postglacial slip increase along the fault. But of course, we need a longer paleoseismic record. While these trench studies are terrific at documenting the most recent one or two, or in the case of the Buffalo Bowl site, 3 earthquake events, we know there must have been more earthquake events to have generated that much offset in the last 15,000 years. So we need a longer record. And that is really what has promoted these questions here that we're going after, is the complete record of past earthquakes at Grand Teton National Park along the Teton Fault recorded in geologic archives? And if so, what is the timing and frequency of these major earthquake events? And so for that.
Question, are you saying because of the weight of the glacier in the valley, it held the slip movement back and then melted and that released energy? Or
yeah, so there was a question about the relationship between unloading of the crust and earthquake. Yes, so essentially, yes, the unloading of this giant mass of ice, or in other cases, it could be just lakes themselves, giant pluvial lakes, like think of the ancestral Great Salt Lake and other lakes of that magnitude. When that mass is released, either through melting glacial ice or evaporating water, the lithosphere flexes in response to that. There's isostatic rebound, and that rebound changes the stress field along these faults. And it's been demonstrated through empirical evidence and models that can result in a more rapid slip rate along the fault over a certain period of time. So we're looking to these lakes then to maybe add a little piece to the puzzle. And you may be asking, why lakes? So lakes are incredible at collecting sediments or mud. I know many of you have walked around lakes or swum in them, and you've probably walked through mud at their base. And that's because lakes continuously accumulate sediment from their catchment and maybe beyond. And that sediment, whether it's mineralogic material sand, silt, and clay, or organic matter from plants or organisms living in and around the lake, or maybe volcanic ash or charcoal from a wildfire. All of these things get washed into the lake and eventually deposited and preserved on the lake bottom. And so these sediments record changes in environmental conditions or maybe surface processes, tectonic processes through time. Lakes in seismically active regions can preserve indirect evidence of shaking, of earthquake events, because shaking can destabilize slopes. It can cause slope failures and landslides and rework or mobilize sediment that gets remixed out into the lake basin and then will eventually, again, deposit and be left as a preserved diagnostic layer or horizon in the mud at the bottom of the lake. And so here in the Tetons, and I should say, lake-based paleoseismic studies have now been targeted in regions around the world to try and use lake sediments as another way of reconstructing past seismic activity. Here in the Tetons, they're particularly well suited for this because of this distinctive glacier geomorphic setting and the tectonic setting. These range front lakes, those lakes positioned right along the front of the mountain range here. For example, this is an aerial photograph of Jenny Lake at the base of Cascade Canyon. These lakes are sitting right along the fault scarp, in some cases directly on the Teton Fault. They're positioned in these over-deepened glacially excavated basins, impounded by steep-sided, poorly consolidated moraine ridges, which are prone to failure. And then in many cases, the fault itself runs along their inflows along the western shoreline. So many of these valleys are being fed from the mountain catchments to their west, which those streams create inflow deltas. And of course, those deltas are essentially sitting at their angle of repose, and they're poorly consolidated sands and other material that is, again, prone to failure. Yeah, Mike.
So I'm assuming that the record that you would get, like out of Jenny Lake, would only be since deglaciation, because prior to that, the glacier would have scoured the whole basin.
Yeah, terrific question. The question was related to the age or the time span of these lake deposits, essentially when these lakes formed. And Mike is absolutely right. These lakes formed only when the glaciers that carved these basins began to retreat. So lake inception begins with glacial retreat from those terminal moraines, which are shown in that bottom map figure there. For that same figure of the LiDAR, showing those giant terminal moraines. In fact, you can see all of the nested ridges, kind of the concentric ridges of those terminal moraines. And that speaks to kind of how long the glacier was occupying that general location, but pulsing back and forth, of course, in response to climate change that was operating during the last ice age. At the end of the last ice age, the glaciers retreated irreversibly back to their catchments, and in most cases completely disappeared. Right? There are a few small glaciers occupying the very upper regions of Cascade Canyon, but in some of the other canyons, there is no glacial ice of any appreciable size. And so when those glaciers eventually retreated from the lake basins and never came back, that's when the lake sediment record begins, roughly 15,000 years ago.
I have a question. Now, some people claim that the whole valley was full of ice. Okay. And I don't know where any terminal moraines occurred with those falling out of Yellowstone and south through Jackson Hole. Okay. Now, why would you not consider those recessional moraines rather than terminal moraines, since the whole valley was full of ice?
So there was a question, for those of you on Zoom, a question pertaining to the multiple phases of ice advance during the last ice age and during the penultimate ice age and those before that. We know indeed that, for example, during the penultimate ice age, the Bull Lake glaciation, there was glacier ice that ran right through the town of Jackson all the way down almost to Hoback. During the most recent, or the last ice age, the Pinedale glaciation, ice never made it that far down the valley. There was basically, it's been shown by Ken Pierce, was kind of the pioneer, sort of the grandfather of these glacier chronologies of the greater Yellowstone ice cap. During the last ice age, the ice cap advancing from the Yellowstone Highlands and from the Gros Ventre, did indeed advance down into the valley of Jackson Hole in basically 3 phases, but it never actually advanced down past this region that I'm showing you here. It stopped just north of Jenny Lake here. And so it didn't quite make it down past these lakes. So these are indeed terminal moraines. As you go further north, and I crop that out of view, to lakes such as Lee Lake and Jackson Lake, that ice cap indeed ran right down, and any valley glaciers coming down from the Tetons would have merged with that much larger ice system, and in some cases may have modified what would have become the lake sediment record, or certainly the morainal record.
Right. Because you have the potholes area just south of Jackson Lake, which indicates where
Yeah.
it tapped off the depression.
Yeah, I don't, just south and a little bit east of Jackson Lake. Yeah, I think in some of, hold on to your question and I'm happy to talk a little bit more afterwards, but I think there's some more imagery that that might, I could show you some of these terminal moraines of that northern ice cap that was advancing down. But speaking to the age of these lake sediments, I put together a little flip book here that I think could help us understand this relationship between the formation of these lakes and the timing of deglaciation. So you could imagine that any of these valleys, let's pretend this was Cascade Canyon, during the Pinedale glaciation. Of course, the valley would have been occupied by a large valley glacier that advanced all the way down to the floor of Jackson Hole and created that terminal moraine complex outside of that over-deepened basin, right at the mouth of the canyon. Then in response to warming or drier conditions at the end of the last ice age, of course, the glacier, the Paleo Cascade Glacier, began to retreat. That's when this particular lake, in our case, Jenny Lake, was born. Ever since that lake formed, it's been constantly accumulating sediments, which I've tried to demonstrate here with those dashed lines in that blue lake there. During the timing of deglaciation, most sediment delivered to the lake would have been sourced by that retreating glacier. And so we would expect that sediments dating to this time period would really reflect this phase of deglaciation, which, as I said before, continued quite rapidly all the way to the upper elevations of the canyon. In some other cases, maybe, for example, an Avalanche Canyon, there are some mid-canyon, mid-elevation lake basins that are exposed and that exist today. And then maybe some cirque lakes at some of your favorite hike-to lakes at the higher regions of the canyon, maybe like Lake Solitude. And then, of course, this has been the conditions that have persisted for much of our present interglacial, which we call the Holocene. So with all of that, we generated this hypothesis that past earthquake events along the fault would have generated different types of slope failures, including these inflow delta failures, subaqueous gravity flows, slumps, and landslides. And to test that, we went out to multiple lake basins along the fault to collect sediment cores and to map the sub-bottom stratigraphy using geophysics. So we targeted these 5 lakes here from the south: Phelps Lake, Taggart Lake, Bradley Lake, Jenny Lake, and Lee Lake. And those are just the core sites that we targeted. So these geophysical surveys that I mentioned were done where we sailed around the lake surface, towing a acoustic sub-bottom profiler device to map the distribution and thickness of lake sediments, which you can see here nicely expressed in the bottom of the lake here. All of these well-bedded horizontal laminations of lake sediment stratigraphy, which in this case are burying this sort of unconformable, chaotic reflector here associated with some sort of slump or landslide deposit buried by those lake sediments.
What's roughly your vertical scale?
Yeah, great question. I don't have a scale. So the question was related to the scale of that seismic transect. The vertical scale there, this is something like 12 meters. Maybe my cursor is probably about 5 meters tall. And then the horizontal scale, maybe this is a kilometer or so. Yeah, it's great data. What we were trying to mimic was a study done in and around the Lake Tahoe region, which had used seismic imagery in conjunction with sediment cores to target these seismic deposits there, which they highlighted with those different colors. And then, of course, we were needed to collect the lake cores themselves. So with each lake, we went out usually in winter when the lake is frozen over. It provides much more ease of access and allows us to kind of set up all of our coring equipment on the lake surface without worrying about falling off a boat or keeping a boat anchored in place. So yeah, we head out onto the lakes, auger a hole through the frozen lake surface and lower down some type of contraption. We've used various different coring systems on these lakes. They're deep lakes. For example, this is, that looks like Taggart Lake. Actually, Taggart Lake is not that deep. Taggart Lake's a shallow lake. That's about 25 or 30 feet deep. But some of these lakes, Phelps Lake, Jenny Lake, Lee Lake, are over 200 feet deep easily. And so to remain fixed in one location, anchored on a boat can be difficult, particularly if it's windy, for example. So because these lakes freeze over predictably, and for most of the winter, we've decided to perform the coring in the wintertime or the late spring, right around now, actually. The conditions on the lake look just like this. I flew in over them yesterday, and they're not quite melted out, but they're beginning to look a little bit more gray and blue. So here you can see that's a long aluminum tube in this case, and it's basically just a glorified straw that we lower down on cables through the water column and then use a hammer attached to the top of it to kind of pull up and drop down and percuss or hammer that tube down into the mud. This was one of the earlier field seasons. We've since transitioned to a much burlier coring device that involves this 15-foot tall tripod and multiple cables and a much stronger tube, which is shown in that center image, and go down in a series of successive 2-meter drives into the same hole. So we'll hammer 2 meters, pull up that core, extrude it, package it, and then go right back down the same hole and get the next 2 meters and the next, and so on, until we basically hit refusal, until we hit that glacial till gravel or boulder layer at the very bottom of the sediment fill, or until some other anomalous deposit stops us. So many field season involving dozens of people and student teams out on these lakes over the past nearly 10 years now. Yeah, question?
When you're driving your core down, how do you know how far it's been driven down and when you reach refusal?
Yeah, the question was, I laugh because the second part of that answer to that question is humorous. The question was, how do we know how far we've driven an individual drive? And then at the end of a drive or during a drive, how do we know we've hit refusal and that there isn't more sediment down there? To answer the first part of your question, yeah, we're measuring out the length on these cable spools. So we measure the water depth. We know exactly how far we can core based on the tube length, and then how far we ended up coring on the previous drive. And we just do all the arithmetic and flag the cables, so to speak. In terms of hitting refusal, knowing when we can't go any further, that there's no simple answer to that. It's really this kind of balance between when I feel like we're about to destroy the equipment, or I feel like we're not able to go any further. So oftentimes, yeah, we'll hit dense layers or perhaps gravel layers, as we'll see associated with these earthquakes, which can stop us for a little while, but we can punch through them. So it's a question. It's always a question. Yeah.
Another potentially humorous question would be, how do you know you get it back in the same hole?
Yeah. So question of if we're going down in successive drives, how do we know we're re-entering the same exact hole? In some cases, it doesn't really matter. So if we're really good with our depths, we can offset those drives and assume that even if it's not exactly in the same hole, especially in those upper few meters of sediment that are relatively low density, and in some cases the hole will collapse, or maybe we won't enter the same hole. We can keep pounding until we get to our desired depth without allowing any sediment to enter the tube. Yeah, it's a really specialized system that has this metal piston that has these flanges that lock at the front end, the driving end of this steel barrel. And so we can just drive it down until we get to the exact depth we want, release those flanges, and then begin coring there. Once we get further into the sediment fill, the sediment gets so dense that you can actually feel it. Even from 300 feet above, you can feel when the core belt finds the hole and then goes down, because it's almost impossible to just blast through meters and meters of core. You need to be in the hole. So yeah, you kind of get a feel for it.
So you don't have a funnel simulator.
They do make funnel. They make re-entry cones for this exact type of thing. That's exactly what they do in the marine coring world.
A little hard to get through the ice.
Yes, that makes it difficult. But folks, colleagues who do this similar type of coring on similar large lakes will do it in the summer from a boat and use re-entry cones. Yeah.
Roughly how much sediment do you go through?
It depends on the lake. Meters. So yeah, from maybe 5 meters, depending on the location in the lake also. And that goes back to us wanting to map the stratigraphy here.
Sure.
So it varies between, say, 5 meters to 15 meters.
Do you test cores for radiation?
Do we test cores for radiation? No, not. Yes and no. We measure the, we use short-lived radioisotopes, including the cesium-137 spike from above ground nuclear bomb testings in the 60s, in the very upper few centimeters of these multi-meter long cores, to try and generate an age model for the past few decades. But otherwise, no, we don't. But I'd be happy to hear more thoughts about that at the end of the talk. Okay, so I was showing you images of Jenny Lake. I thought that would be a good place to start. I know we're going to move right along here. I really do appreciate these questions. That's great engagement. But in fairness to the folks on Zoom who might also have questions, we should keep going. So here's a map of Jenny Lake where I've overlain the LiDAR elevation of the landscape, as well as highly resolved bathymetric data that we collected with a multi-beam sonar. So that's you can think of that as the topography of the lake floor at high resolution. So this again is a moraine bound lake there. It's roughly 75 meters maximum depth, with an average depth of more like 40 meters probably. And it's at the base of Cascade Canyon. Bathymetry and seismic imagery reveal a complex lake floor morphology associated with glacial and tectonic processes. And so here I've just put some more detail on that map figure. I've shown the trace of the Teton Fault there running along the range front, offsetting those Pleistocene moraines, and then running underneath the lake itself, right at the mouth of the canyon. I've also shown in yellow there that the age of that terminal moraine complex, as determined by Licciardi and Pierce back in 2008. And that dates to about 14.4 thousand years ago. So to go back to Mike's question about the age of the lake, that there is one of our constraining ages for determining not just the timing of deglaciation at the end of the last ice age, but the age of Jenny Lake itself. And we did a similar thing for all of these lake basins. I've also shown here the locations of a variety of core sites, as well as the seismic transects shown by those black gridded lines. And then interestingly, at Jenny Lake, there are two lake terminating landslides that initiated kind of on the mouth of the canyon itself, both on the southern and northern wall of the canyon. And we dated those landslides, which were triggered on the hill slopes above the lake, and then ran out into the lake and were deposited in the lake bottom as those large block and fan deposits that I tried to highlight with that teal dashed line. And we dated those features on land using cosmogenic radionuclides, the same exact nuclide used to date the moraine itself, and the ages for those two landslides are shown there.
Are the yellow dots on land where you cored on land?
Those are the ages of bedrock and boulder samples in those landslide paths. So those are the sample sites we use to determine these dates here. And those are all in kiloannum, or thousands of years ago. just to show you some of the beautiful seismic imagery. Also, here are those two seismic transects highlighted in bold from A to A prime, so from the mouth of the canyon to the eastern perimeter of the lake, shown in that top panel, where we actually capture the Teton Fault scarp itself, offsetting those conformable lake sediments. We can see that landslide deposit, as well as that shoal along the eastern perimeter. And then there's a kind of a north-south transect going along across the lake's central deep basin and to the shallow southern margin of the lake. So to show you what some of these cores look like, again, we've done this process now at all of these lakes. We've collected well over 100 meters of lake sediments. Here are two cores from kind of the central site in Jenny Lake, two sister cores, 1A and 1B. So when we're out there, we collect these cores in an overlapped manner so that we can cover any core breaks with a sister core. And so 1A and 1B are just taken maybe 2 meters apart from each other. What you can see in both cases, in terms of Jenny Lake, going back to the question about the thickness of lake fill, at this location in Jenny Lake, it's about 6 meters or so of lake sediment. And it's kind of this two-part sequence where the older sediments, those are shown here on the right, and it gets younger towards the top, which is shown here. So the oldest sediments are these laminated, light gray, clay-rich glacier sediments, which again correspond to that timing of ice retreat when there was still a glacier in the valley, but it was retreating through time, and eventually the glacier melted. And instead, we have non-glacier sedimentation persisting through our present interglacial, through the Holocene. And that's characterized by much more organic rich, lower density brown lake sediments. I've also shown here with these black arrows a series of disturbance deposits, which is going to really be the focus of the rest of this talk. In some of those cases, I've put some ages on those. So on some of the larger disturbance deposits, which as we'll see are associated with these earthquake events, we've put ages on those. And the way we do that is by dating the stratigraphy through a variety of methods. So we use radiocarbon to date organic remains, mostly plant material, terrestrial plant material that's incorporated into the sediment fill and preserved, and we can date those organic remains. There's also a couple of volcanic ash horizons in these lake cores from volcanic eruptions over the last 15,000 years, not really from around here, but from the large volcanoes in Cascadia. For example, I've showed you that this is the Glacier Peak ash, which erupted from Glacier Peak in Washington, roughly 13,600 years ago. And so we can chemically characterize these volcanic ash deposits using their major element chemistry. I've just showed you a table there at the bottom. Then for those very old sediments during that phase of deglaciation, there are annual laminations that are referred to as glacier varves or clastic varves. So we can do annual layer counting just for the first few hundred years of the sediment record.
So can you just kind of describe what we're seeing there, the light and the dark? That's a year. If you start on the right side with it. White.
Yeah, so there was a question about this varve stratigraphy, and I realize I also haven't introduced the figure. What I'm showing here are just 3 intervals from 3 different sediment cores that I thought contained visible organic remains, tephra layers, and these clastic varves. So the panel at right shows these glacier varves. And so those are annual laminations that are composed of kind of a 2-part series that are differentiated based on changes in grain size associated with glacial fluvial delivery of sediment to a lake during the spring, and then the lake or body of water freezes over in the winter, and then very fine sediments can finally settle out of the water column during that ice-covered season. So for example, the reason why glacier lakes have that kind of iconic or characteristic turquoise hue to them is because they're chock full of glacier flour, really fine-grained sediments, which remain in suspension in the water column and refract light and give it that aquamarine hue. When the lake freezes over, all of those fine-grained sediments, which are remained in suspension due to wind turbulence and mixing of the water column, when the lake freezes over, it's so calm that those fine-grained sediments can settle out and form a clay cap, on the sediments below, and therefore you've got your annual cycle of melt season coarse grain deposits capped by the fine grain winter deposits. So you have your annual varves. All right, so now I'd like to focus on the actual evidence we have for the paleoseismic activity, and that's in the form of these disturbance deposits, which in many cases are quite thick, quite obvious, very easy to identify in core section. They can be over 25 centimeters thick, so very large anomalous deposits that exhibit classic turbidite stratigraphy, which includes an erosive basal contact and an immediate deposition of very coarse grain, poorly sorted sands, coarse sands, in some cases full-on gravel, golf ball size blocks that grade upward through finer sands and silts, and then eventually again a clay cap of the finest grain sediments that take the longest to settle out of suspension. So what I'm showing you here is an interval from a core at Jenny Lake that contains 2 of these turbidite deposits here, which can obviously be seen visually on the split core face, but also show up quite well with these 2 physical parameters of mean grain size. So that's the mean grain size of sediments from, in this case, sampled at sub-centimeter intervals, and then also the density, just the basic bulk density of the sediments. So we see that the turbidites in general are much more coarser grained and denser than the background lake sediments. And we see some interesting patterns associated with the evolution of the individual deposit in real time over the course of, for example, days or maybe hours as these deposits were being generated.
What do you make of the variation in your density curve, particularly in the 8.3?
Yeah, that's a great question. So the question was related to that dip in density during kind of the near the peak in grain size. That decrease in density is associated with, and it's hard to see in this image, I think, on the screen, but this particular event, as we'll see, is associated with one of those landslide events that ran out into the lake. And because of that, it contains an unusually high amount of organic material. And you can see it actually if you squint. There's a lot of kind of brown looking terrestrial organic material that's interstitial to those sands. That organic matter is very low density. And so you see a dip in density associated with that lens of organic material, which we think was introduced or transported to the lake only, in this case, only because there was a landslide event, which is not the case for every earthquake deposit. I'm also showing you that how we can date these events, both using the position of these volcanic ash layers, but also radiocarbon dating. So in all cases, we're trying to date these earthquake turbidites at their upper and lower contacts to determine precisely the age of the event deposit. In the interest of time, I'm not going to go into this in too much detail, but here we focused in on 5 of the larger turbidites, and we measured grain size distributions using particle size analyses at relatively high resolution to evaluate this pattern of sediment deposition during the individual deposit event. And again, we see a recurring pattern of this sharp basal contact, suggesting it was a rapid onset of a deposition of coarse grain material. These sands and coarse sands that are delivered way out to the middle of the lake are very different from the background lake sediment that usually occurs over the last 15,000 years. And that's characterized by fine silts and maybe organic material. To transport sand out to the middle of a lake is very unusual. It requires a lot of energy. And so that's what characterizes the base of these deposits. That coarse material is deposited first and forms the bottom of the deposit, and then it fades up to finer and finer sediments and eventually a clay-rich cap. I'm happy to talk more about this if folks are interested afterwards. So we've performed these analyses on all of the cores from Jenny Lake. In this case, it's 4 different cores, and we compile all this data, and we're able to put together a figure that looks like this, where we're showing a time series. So time is on the x-axis here, again, in years before present, in this case, 1,000 years before present. So we're going back a little over 14,000 years. And then running to present day. And these 2 panels here are showing those same 2 parameters, sediment density and in this case, sand grain concentration. And we see these spikes in density and sand concentration that co-align, that are associated with these turbidite events, and we can put dates on these events, and that's what's shown here. I'm also comparing some of these to the ages of earthquakes as determined from trench studies, and in this case, the original trench excavation at Granite Canyon. And so we see a series of earthquakes with a relatively consistent recurrence interval of about 1,000 years, beginning almost immediately after deglaciation and persisting to maybe the mid-Holocene, and then a complete change in character of seismic activity. So we see repeated earthquakes roughly with a recurrence interval of about 1,000 years. And then after that, we don't see evidence for a major earthquake event for potentially the last 5,000 years at this site. So it's quite interesting. We've done this now at other lakes along the fault, so it's important to replicate these data sets with these other lake basins. And so I'm showing that here. We've done this at Phelps Lake, at Taggart, Bradley, and Lee Lakes. And on the bottom, and so that's the maps of those individual lake basins I'm showing there. They're very similar to each other. They're all impounded by these terminal moraine complexes. The fault runs along their western boundary. They're positioned right at the mouth of their respective canyons. To speak to the question you had earlier, this lake to the north, Lee Lake, you'll notice has a very different moraine complex around its eastern perimeter. And that refers to the question we had earlier about the advance of the northern Yellowstone ice caps southward into the northern part of the Valley of Jackson Hole. And these features here mark the southern extent of that advance.
Just kind of smeared it out.
Yeah. And then on the bottom, I'm showing you there just the time span of the cores that we recovered from the different lakes. To go back to the question we had before, how do you know when you hit refusal, and what does that mean? With Lee Lake, we indeed hit refusal. We could not core anymore, but we certainly didn't make it to the bottom of the sediment fill. We hit what we interpret as one of these earthquake deposits, and it's very difficult to core through sand and gravel, as you can imagine, without some sort of rotating auger type device. To just try and pound through it is very difficult. So that nearly broke, we almost broke the coring system on Lee Lake. But the remainder of the sites, we were able to span the entire postglacial record. Interestingly, depending on the individual location, whether we were on a slope or in the center basin, we have some slight differences in the core stratigraphy. Oftentimes, cores collected from a slope contain unconformities, which are gaps in the record that are developed when that slope fails and sloughs off, much like an avalanche occurring on a hill slope here during the winter time. And so a package of that accumulated material sloughs downhill, and then with continued sedimentation, or in this analogy, snowfall, you would bury that, but you know you have a gap in the record, and that material is actually preserved in the center of the basin or on the lake floor. So by comparing center basin cores to slope cores, we can kind of piece together this history of slope failure events and deposition in the center basins. And so to now inundate you with all of these dates here, here's just I put a list of, so again, these are 5 different lakes. Each lake has multiple cores. There's a tremendous amount of data that this is not published yet. We are still working this up. But here's a list showing the age of these disturbance deposits and then the lakes that they're identified in, or the abbreviation for the lake they're in. So TL is Taggart Lake, BL is Bradley Lake, and so forth. And we see some interesting patterns where the timing of these events seems to co-align between lake basins. And so that's really encouraging. But in some lakes, we see an event that is not well expressed in a nearby lake. And that's also interesting. That may refer to dynamics of the fault during ruptures. Perhaps the fault is segmented or experiences displacement events that could trigger slope failures in one part of the fault that maybe are not as well felt in another part of the fault. Perhaps there's other faults in the region that are creating shaking that's felt more strongly in one region or another. So it is encouraging, though, that some of the more prominent deposits show up in all of the lakes, and these are those that line up with the ages of those faults that were identified in the trench excavations, as well as the age of those two landslide events. That, again, those landslide events on Jenny Lake occurred right above the fault itself on those steep hill slopes at roughly 14 and 8.3 thousand years ago. The age of that event in Jenny Lake is supported by the age of major earthquake deposits in these other lakes as well. All right, so we'll summarize and then I'm happy to field some more questions here. So the spectacular landscape of the Tetons, which attracts so many millions of people each year to this incredible place, is attributed to the competing or the integrated influences of surface processes and of course uplift along the Teton Fault. Previous studies have suggested that the prominent fault scarps that are visible along the range front were generated by a series of earthquake events during the past 15,000 years. And while this iconic scenery has perhaps benefited from this fault activity, the potential for future large earthquakes and related slope failure events presents obvious hazards to visitors and infrastructure and resource management efforts. And so this study demonstrates that lake sediments in these Teton lakes present a really great opportunity to construct continuous and well-dated records of these past seismic events, and ongoing work aims to finalize the chronologies for all of these individual lake records, synthesize them with existing trench and modeling efforts to understand fully the postglacial history of the fault and perhaps apply these techniques to other faults in the basin and range. So with that, I'd like to say thank you and stay tuned.
Let's let the Zoom screen come up. Let's take some Zoom questions since we basically dominated all the questions. And let's give Cynthia a chance to ask the questions.
And you use the hand power elevator.
Okay. Cynthia,
Cynthia should unmute.
Yeah, I'm unmuted. I'm trying to spotlight myself.
There you go. Good to see you.
Okay, great. Thanks, everybody. Get back to chat now. So
You're here.
sorry.
Three more questions.
So one question is related to the fact that the lakes freeze over in the wintertime. And so are we missing some records of seismic events because the sediments are restricted from getting into the lakes by the ice?
Interesting question. So absolutely, these lakes freeze over for in some years more than half the year, and it's very likely that many of these earthquake events, or just based on that fact alone, we'll say they're frozen for half the year. It's possible that half of those earthquake events would have happened in the wintertime when those lakes would have been frozen over. Of course, during the evolution of this Holocene climate, the duration of ice cover may have changed through time, but it's very likely earthquakes occur during the winter as well. The fact that the lakes freeze over doesn't necessarily preclude them from being sensitive or recording earthquakes that occur during that time they're frozen over. So in many cases, we hypothesize that the sediment source that's being deposited as these diagnostic disturbance event deposits is really previously accumulated lake sediments that are deposited along the perimeter slopes and the inflow delta of the lakes themselves. So while the lake water might be frozen and perhaps the inflow streams are more limited in delivering sediment, it's not the sediment that's being delivered in real time when an earthquake happens that's forming the deposits. It's the accumulation of previous sediments in and around the lake shore and on the lake slopes that gets mobilized, reworked, and eventually deposited as one of these turbidites. So I don't think that is a limiting factor in the sensitivity of these lake records in recording seismic activity.
Deeper lakes aren't frozen.
Absolutely not. So the lake, there was a question here about the thickness of lake ice during the winter. And that last slide I showed you there was a picture of our ice auger, which I don't know, was something like 20 feet tall. That was to auger through some of these high elevation lakes where we're really not augering through lake ice. It's mostly a snow that we still need to auger through. It's kind of refrozen snow and slush. And the lake ice itself, whether it's on these high elevation lakes or down low here, is always less than a meter of actual lake ice. It'll be sometimes only 50 centimeters, 40 centimeters of actual ice, and then this kind of stratigraphy of refrozen snow and slush ice.
Of course, if you have
Let's let Cynthia ask some more questions.
Okay, thank you. So there was actually an acknowledgement. So John Bird wanted to say thank you for acknowledging his early work at Granite Canyon.
Well, that's terrific. Thank you, John. I'm just honored that you joined that talk.
Very nice. So a question about a big earthquake on the Teton Fault. The question is, would the magnitude be significantly less on the Idaho side than on the Jackson Hole side?
That is a great question. It would depend on where exactly along the fault the earthquake occurred, but I'm not sure I fully understand the question in terms of distance from the fault, or some sort of shielding by the mountains from the seismic waves themselves.
I think it was more the latter, sort of, would the shaking be worse on the Jackson Hole side versus the Idaho side, is my reading between the lines.
Yeah, that's what I would, that's what I personally would suggest, but there are certainly folks in this chat or in this room who could answer that question in greater detail than myself. So if for example, John Bird is still on and he wants to answer that, that'd be great.
Well, we're only doing questions by chat, so we're not actually allowing participants to ask questions via Zoom.
It's a great question. I would lead the questioner to the University of Utah seismic group's webpage, where they have shake maps and all sorts of information regarding the potential hazards of future earthquakes in the region, both here and all along the Eastern Basin and Range.
Oh, great. Okay.
That's
Thank you.
Bob Smith's group at Utah.
All right. And then a different kind of question. This is related to the thermal uplift of Yellowstone. Does that thermal uplift and height of Yellowstone buoy the northern portion of the footwall of the Teton Fault, and then possibly reducing fault slip in the northern portion of the fault?
That's a great question, and certainly one that is target of ongoing research. What we tried to do in the this initial study from Jenny Lake published in 2019 is we tried to associate the timing, to determine if there was an association between the timing of these earthquake events and evidence for inflation or deflation cycles of the Yellowstone magma chamber, which that record is, it's really interesting how that's been pieced together by dating paleo shorelines of Yellowstone Lake and at the head of the Yellowstone River, trying to determine periods where the lake itself was being essentially tilted in response to inflation or deflation of the underlying magma chamber. And the ages of that study of these kind of the Yellowstone plume breathing, so to speak, or the magma chamber breathing, seem to maybe correlate in time to periods of fault activity here in the Tetons. So it does appear that more work has been performed to suggest that these external controls on Teton fault activity seem to be maybe governed by this ice unloading factor. It's very likely that another external control could be the activity of the nearby Yellowstone volcano. Absolutely. But it's a great question.
Sorry about that. So just a couple of comments came in, one from John Bird and another that's propose that the shaking in the event of a major earthquake on the Teton Fault would be worse on the Jackson Hole side.
Did you look at the fault scarp just west of, what is that, the North Lake, that shallow lake? There's a definite fault scarp there.
Is that Lee Lake? Lee Lake?
No, it's between Lee Lake and Jenny.
String Lake?
Oh, String Lake. Yeah.
It's on the west side of String Lake.
Yeah.
There's a fault scarp there.
Yeah, really. So there's been a question here about that prominent fault scarp above String Lake, that flowage between Lee Lake and Jenny Lake. Yeah, particularly at certain times of the day, you can really see that fault scarp expressed on the hill slope there. And in that region in particular, from Jenny Lake through String Lake, that region has some of the tallest fault scarps throughout the range, suggesting that, and recent studies have demonstrated that there's kind of a pattern of fault displacement as you go from south to north along the fault trace. And the highest rates of displacement are right in the center of the range. And that has been recognized for a long time and actually been suggested to correlate to the fact that the highest elevations are also in the center of the range. And so maybe that lines up where the fastest slip rates and most fault displacement are associated with the highest mountains.
Do you guesstimate how rapidly the fault block rose out of the ground initially?
During each, so this has been occurring over millions of years now through individual earthquake events. And those earthquake events, at least over the last 15,000 years, as has been demonstrated in these fault trenches, result in vertical displacements of say 1 to 3 meters of displacement. So it's a accumulation of what, when we think of the total displacement, it seems like really small increments, but in real time, those are large earthquake events.
Right, because we could consider catastrophic displacements. I mean, of magnitudes far greater than what uniformitarian ideas are.
Yeah. Yeah.
We need to let Cynthia ask some more of the Zoom questions.
Go for them.
Actually, we're pretty much done with the Zoom questions. So I think it helped. Oh, wait a minute. Here we go. I'm just going to read this. But it says, but the drainage divide does not reflect a differential uplift. And if the drainage divide is Pinedale, then the variations in displacement along the front have not yet migrated back into the range. More likely that the cathedral group is an inherited uplift from the Buck Mountain Fault. It's not really a question, but.
Thank you. Yes.
What's the status of future field work versus analyzing the tremendous amount of data that we have?
Yeah, thanks, Peter. We have so much data in-house that we're working through now. So this particular year, this is the first year in almost a decade that we haven't collected any new sediment cores. Yeah, but we are hoping to perform some additional seismic surveys at the very end of the summer. So kind of conditions permitting and pandemic permitting. And that has, I should say, that has been a challenge also, of course, is to be conducting this type of work during the pandemic. And we've had a full remote year last year, and it's been a challenge. Yeah.
Where will that be? The seismic.
So we're hoping to do that at Lee Lake and Phelps Lake. Lee Lake is a really interesting site because the fault runs right through kind of the center of the lake itself. And so that would be a really great opportunity to evaluate the fault offsetting these lake sediments, which if we can then date them directly, we might be able to get better estimates on the kind of the magnitude of these individual events.
So it looks like we're kind of done with the Zoom questions, but a lot of appreciations and thanks rolling in from the Zoom audience. We had at least 49 people on Zoom. So thank you, Darren.
Yeah, thank you, Cynthia.
You get about 20 in the, 16 at least here in the room. So, we're gonna.
We're about to break up.
So if there are no more questions, I want to thank Darren
Thank
for
you,
a
Mike.
terrific presentation.
Thank you.
This is small, token of our appreciation.
Thank you.
We all like rocks. And absolutely awesome. I mean, just from the macro to the micro, you hit it all.
Yeah, thank you.
So thank you very much on behalf of both the Zoom audience and our in-person audience. Darren will be here for a minute if there's a question that you just thought of.
Yeah. Okay, thanks. And thanks everyone again. for
2
coming.
weeks,